Ridgetop Group Incorporated is the leader in prognostic and diagnostic technical approaches, providing solutions for optimized subsystems and systems for aerospace, industrial, automotive, and energy applications. Ridgetop is a Tucson, Arizona-based AS9100C and ISO 9100-2008 compliant company with a diverse staff that provides high-quality, innovative prognostic innovations that set the standard for the industry. Today, Eric Moser, one of our many experienced systems engineers, is providing an introduction to NightHawk, the no-fault found reduction software tool that will set the new standard in anomaly detection.
NightHawk is an interactive tool suite combining data and information management with advanced data analysis techniques, serving to address root cause, reduce and/or eliminate, no fault found, could not duplicate, retest OK, and other similar issues related to circuit card assemblies and modules in complex critical systems. The root causes leading to NFF are linked to gaps in test coverage, operational usage conditions, and aging effects, which, due to their very nature, are difficult to identify using conventional approaches. NightHawk employs an interactive user interface to allow the use of various algorithms for the detection and isolation of anomalies that are otherwise hidden from traditional testing approaches. These algorithms can be used to enhance existing test program sets, or can be incorporated into new test programs. Information about each CCA is stored within the NightHawk environment. Board photo shows an actual image of the board and allows users to associate component labels with each part of the board. Schematic is an up-to-date layout of the board's electrical internals. Layout shows the physical component locations and reference designators on the CCA. Specifications describe the purpose of the board and how it fits into the rest of the system. Maintenance records describe the specific CCA's repair history. BOM shows the board's bill of materials. TPS allows the user to generate and edit test programs and also interface with the automated test equipment. Each algorithm can be used in either development or executable form. Development form is useful for evaluating an algorithm's capabilities for particular datasets. It can be used to determine if an algorithm is suitable for use in a specific scenario. The user opens the algorithm's development interface, opens a file containing the input data they would like to process, fills in the appropriate inputs, and runs the algorithm. The program typically places the output into a separate file and displays it for the user to view. Executable form allows the same algorithm to be called from a test program set. The appropriate data and inputs are passed to the function, which then processes and outputs the data to a separate file, accessible by the test program. NightHawk's Interpreter allows rehosting of existing test program sets and generation of new test program sets. It's a simple script language that's easy to learn and understand. Test program sets are contained as script files and can be run at any time. Also, Ridgetop's algorithms can be called from the script language using function calls. Test program sets are associated with particular circuit card assemblies. The data for these circuit cards is also kept within the NightHawk environment and is easily accessible from a series of tabs. Today I'm going to demonstrate the capabilities of NightHawk using an example circuit card assembly in both normal and faulty operating modes. This board is a composite sine wave generator, and its functional output is a composite sine wave with low frequency characteristics. Two frequency modulators alter the period of the voltage controlled oscillator output. This output is fed into two separate dividers, which are then fed into two separate sine wave generators. The output is summed together and a DC offset is added. The circuit's behavior must fall within the listed specifications, otherwise it is either out of calibration or faulty. The board has two connectors. The first serves as a functional interface. This is the connector that outputs the composite sine wave and interfaces to the rest of the system. Power is supplied through this connector as an input to the board. The second connector is a built-in test connector. This allows external automated test equipment to access test points internal to the board. In this case, this example board only requires a power input and outputs a composite sine wave. We start by running a test program which may be used to test a board like this. The board begins with no faults and is calibrated to specification. This means that no fault should be detected. The test is the frequency modulator B test. This test ensures that frequency modulator B is varying the VCO output within the proper range. As can be seen, the test passes as it should. We also run a ridgetop enhanced version on the same setup to show that the board passes. We now insert a faulty Zener diode. This causes distortion in the sine wave output. However, the original test program does not test for this, and so does not detect the fault. To resolve this, the ridgetop enhanced test used our algorithms to not only detect a fault, but to isolate the bad component. This reduces no fault found, could not duplicate, retest OK, and other issues commonly seen in circuit card testing. NightHawk is a comprehensive tool for reducing issues commonly associated with circuit card assemblies. It has a rich feature set, which allows the user to approach test program development from many different angles. There is a recognized need to improve the fault coverage of complex aerospace, automotive, and complex industrial systems, and NightHawk is a solid solution to these problems. Please visit ridgetopgroup.com for more information and to contact us. Thank you for watching.